Hello everyone, my name is Maxime Chevalier-Boisvert, and today I'll be telling you about the lightweight intermediate representation in Backend that we've been building for Yjit. So first, I'll give you a little bit of background on Yjit and how it works. Then I'll talk about the motivation for building a new backend. After that, I'll cover the design of the new backend, then current performance results, and finally, I'll talk about some next steps to unlock even higher performance. Yjit is a project that was started 2 years ago at Shopify to build a new Yjit compiler inside of Ruby. From the start, Yjit has been open source, and this was very important for us that Yjit be open source because we were hoping to eventually upstream Yjit into Ruby. Our focus and our goal has been to get double-digit speedups on our real-world Ruby software. In particular, we focus on web workloads and Ruby on Rails because Shopify has a lot of infrastructure running on top of Ruby on Rails. And the Yjit team tries to take a data-driven approach to optimization. That is, we have a large, diverse set of benchmarks. We benchmark often, and we gather detailed metrics. Speaking of the Yjit team, I wanted to give a big thanks to everyone who's contributed to the Yjit project, both at Shopify and at GitHub, and also including open source contributors. This project would really not have been possible without the help of all of my very talented teammates. So I gave a talk last year at RubyKaigi 2021 titled Yjit, Building a New Yjit Compiler Inside of Ruby. Following this talk, we were invited by Ruby core contributors to submit a proposal to upstream Yjit as part of Ruby 3.1. And thankfully, this proposal has been accepted. Yjit has been merged and is now officially part of Ruby 3.1. So some of the features of Yjit are lazy code generation. That is, we only compile pieces of code that actually get executed at runtime, and we can compile only parts of methods that get executed. Yjit also linearizes the machine code that it generates. That is, it tries to generate straight line pieces of machine code that naturally fall true to minimize branching. Yjit is able to do runtime value promotion. That is specialized code based on values that are happening at runtime. It can also specialize machine code based on types that are observed at runtime. And it can do speculative optimization and de-optimization. For example, we can speculate that bops will not be invalidated. So that is, in Ruby, you can redefine methods on integers, for example, but Yjit is able to speculate that this will not happen. So it doesn't need to constantly check that these basic operations are not redefined. Yjit also implements polymorphic inline caches, and this applies to call sites, but also set instance variable and get instance variable. Lazy basic block versioning is an alternative just-in-time compiler architecture. So traditional just-in-time compilers are method-based. That is, they compile entire methods at a time. But basic block versioning operates at a lower level of granularity, where it can compile only the parts of methods that get executed. It's a lightweight technique that works by interleaving execution and code generation and can generate machine code very, very fast. This came up as part of research work that I did during my PhD at University of Montreal, where I built Higgs, an optimizing just-in-time compiler for JavaScript. The focus of my PhD was to optimize dynamic languages and in particular eliminates dynamic type checks. Basic block versioning allows us to do type specialization without doing traditional whole program analyses, because these kinds of type analyses are very, very expensive. And basically the idea here is that we're going to let the program tell us what the types are at runtime instead. So there are two key components to lazy basic block versioning. The first is the versioning of basic blocks, which allows us to accumulate and propagate type information and specialize machine code based on context. So we can do selective tail duplication to unfold the control flow graph. I'll note here that the goal is not to create multiple versions of code. The goal is actually to use the versioning of basic blocks as a tool to propagate type information. The second component of lazy basic block versioning is the laziness. So being able to generate code lazily. So we generate code only when it's needed, truly just in time. We compile pieces of code only when we know for sure that they're just about to get executed. So for example, if we have an if and else branch, we're only going to compile the side of the if and else branch that gets executed. And by doing that, by generating code lazily, we're able to capture type information as late as possible. So we do lazy tail duplication, and it's a little bit like lazy evaluation for code. Compared to interpreters, JIT compilers look like advanced, sophisticated technology from the future. And so it might seem like by just adding a JIT compiler to CRuby, we might get a sleek, fast, and powerful machine. But in reality, what we ended up with looks a little more like this. It's faster than before, but maybe it's not as nicely integrated as it could be, and not as fast as it could be. And so this year, our focus has been on building something more powerful. We've been working hard to put in place the foundation to build many enhancements to Yjit, but doing so required a little bit of engineering. All of this effort is worth it though, because we want to build something much more capable and powerful and truly unstoppable. The Yjit team has many great improvements in progress for Ruby 3.2, including porting Yjit to Rust, finer granularity constant cache and validation, optimizing the rendering of ERB templates with Yjit, the integration of object shapes into CRuby, a system to garbage collect machine code generated by Yjit, and of course, the new backend for Yjit, which is going to bring ARM64 support. And of course, the focus of this talk is on the new backend. One of the main objectives with the new backend was to bring forward ARM64 support. In particular, we were interested in having support for Apple M1 and M2 laptops. Basically, everyone in Shopify is running on Apple hardware, and so this was a fairly immediate concern for us, because many developers at Shopify were not able to run Yjit locally. And ideally, what we'd really like is for developers to be in the habit of always running Ruby with Yjit enabled. If we're in a situation where developers have to run Ruby without Yjit locally, but they have to remember when they're deploying that they have to run Ruby with --Yjit, that's not really optimal. We'd like for it to be basically a no-brainer for developers to always run Ruby with Yjit enabled. And this is maybe even more of a pressing concern because soon basically all Apple hardware will be running on ARM64. And so if you have no ARM64 support, you have no Apple support at all, no access to any Apple hardware except through emulation on Rosetta. Of course, having support for ARM64 doesn't just get us support for Apple hardware though. It also brings us support for AWS Graviton instances, Raspberry Pis, and of course, there's some expectation that ARM64 hardware is going to make even more headway into the server space eventually. There's also a question of future-proofing. Basically, one day we might want to have support for RISC-V and other architectures. But of course, the first version of the new backend won't be optimized. There might be some speed up, but it's not going to be fine-tuned, and we think that we can improve this iteratively. So some of the constraints of our design is that for simplicity, we're only supporting 64-bit little endian platforms. We might want to add support for other architectures later, like RISC-V, but this is not an immediate concern for now, and we think that those platforms are similar enough to ARM64 that it won't require huge design changes. We'd like to keep memory usage low and avoid adding extra overhead. We'd also like to minimize the use of dynamic allocations in the backend and avoid expensive analyses. Go for something pretty lightweight. So in terms of a design, we went for a backend that works as a sort of platform agnostic assembler. Basically something easier to work with than platform specific assembly and machine code. The new backend works with linear sequences of instructions. So we're still working one basic block at a time with the basic block versioning paradigm. And our intermediate representation is a flat and linear sequence of instructions. The generated IR is not stored in memory, and so the memory overhead is minimal. That is, we generate IR, but we don't store it after we've compiled it into machine code. And for the compilation process, we do a few O of n passes over the IR, but there's no expensive fixed point analyses. And we use simple register allocation using linear scan, which is fairly fast. So how does Yjit work? Well, initially when code runs in CRuby, it runs into the interpreter. And eventually, if a method is called enough times, we hit a compilation threshold. When this compilation threshold is hit, Yjit installs a stub and starts generating code for that method. But it doesn't compile the entire method at once necessarily. If there's any branches, we install stubs that will call back into Yjit when they're executed. And this is what allows us to compile code lazily. In terms of a pipeline, the old backend looks something like this. So on the one side, you have the CRuby interpreter, and on the right side, you have Yjit. And so Ruby source code gets parsed into an abstract syntax tree. And then this abstract syntax tree gets compiled into YARV iseeks. And eventually, when the call threshold is hit, those YARV iseeks get compiled into x86 64 machine code. Of course, it's more complicated than that. There's a lot of magic going on behind the scenes. And so what we want to do with a new backend is, instead of compiling YARV iseeks directly into x86 64 machine code, we'd like to go from YARV iseeks to Yjit intermediate representation, which we're going to be able to do some optimizations on. And then we can take this Yjit intermediate representation and we can choose to translate it either into x86 64 machine code or R64 machine code, so we can support multiple platforms. And so with our new design, we get a split of Yjit into a front end and a back end part. The front end translates YARV into our intermediate representation, and it takes care of the whole type specialization of code and specializing code based on constants. So the front end is the part of Yjit that implements the lazy basic block versioning. The back end takes care of translating our intermediate representation into machine code, and it also implements some simple platform-specific optimizations. The backend is organized as a series of code transformation or passes. And so we could illustrate the design of the backend something like this. There are some parts of the backend in black that are reused between platforms, such as linear scan register allocation, and also the linking of labels. And then there are some parts in red that are specific to x86 and some parts in blue that are specific to ARM64. Among the passes that are platform specific, we have instruction splitting, the emission of machine code. And so there's a number of similarities between x86 64 and ARM64. Both platforms are little endian architectures that store the lowest bits first. Both platforms are 64-bit, and so they use 64-bit registers and 64-bit pointers. And they have a similar division between general purpose registers and SIMD registers. Both platforms have instructions to deal with 32-bit and 64-bit values. And many of the instructions have equivalent counterparts on both platforms, such as move, comparison, test, add, subtract, multiply, bit shift instructions, logical AND, etc., etc. And both platforms also do comparison and branching in a similar manner using a hidden flags register. So in the design of our new backend, we tried to find a common ground between x86 64 and ARM64. We chose to use a tree address instruction format, where instructions have input operands and output operands. And we tried to abstract away machine registers and work with operand objects instead. When generating code, we use a platform neutral assembler, which we usually call just ASM, the ASM object. And this behaves a lot like the IR builder object in LLVM, if you've ever used LLVM. Finding a common ground wasn't too hard because most instructions we need have obvious equivalents on both platforms, with some caveats that I'll talk about in a moment. The new backend is a pretty good usability improvement over the old backend, because with the old backend, we needed to manually manage things like scratch registers. And we needed to do things like manually move argument values into argument registers prior to a C call. So just to give you an idea what the IR instructions look like, I've listed some of them here. We have a big Rust enum with all of our IR instructions. We have an instruction called breakpoint, which can be used to invoke a debugger in LLDB. This is very useful for debugging. We have another instruction called comment, which allows us to insert comments into machine code, which are then visible when we disassemble machine code. This is also super useful for debugging. We have instructions such as add and subtract, which have 2 input operands and 1 output operand, and this behaves as you would expect. We have bitwise operations such as AND, OR, XOR, and logical negation. We have an instruction called ccall, which takes a list of operands and performs a C function call. We use this to call into the CRuby interpreter. We have comparison and testing instructions, which behave similarly on x86 and ARM. We have some conditional branches, such as jump equal, jump less than, jump if the input is not 0, jump if the input is 0, jump and overflow, which you use for implementing fixed num operations. And we also have some instructions for dealing with memory accesses, such as load and store and move. And of course, there's more IR instructions which are not shown here for brevity, but you can look at the source code if you're curious to know more. But now, this isn't always straightforward to do because ARM64 and x86 are not actually quite the same. ARM64 is a little bit more complicated to generate code for than x86 because it has a number of restrictions. In particular, most instructions on ARM can only access registers and not memory, whereas on x86, a lot of instructions can access both memory and registers. So on ARM, memory accesses must be done through load and store instructions. x86 instructions can branch very far, but on ARM, branch and call instructions have limited jump offsets, usually something like plus or minus 1 megabyte. And also the allowable jump offsets for different instructions are not the same, so that adds some amount of complexity in code generation. The size of allowable immediates is also fairly small. On x86, most instructions can have 32-bit immediates and sometimes even 64-bit immediates. But on ARM, the number of bits for immediates that you can store inside of an instruction, again, varies for different instructions. And there's no instruction to directly load a 64-bit immediate into a register. We also have a situation where some x86 instructions have no direct equivalent on ARM. For example, push and pop and load effective address. And so we have to use other instructions on ARM to enable the same functionality. But it doesn't stop there. There's also a few other things we have to think about. On ARM, we have to manually flush the instruction cache when generating code. On x86, this happens automatically. The unfortunate thing is that this actually incurs a little bit of a slowdown on ARM as well. And maybe the most annoying thing is that x86 and ARM instructions aren't actually in the same format. ARM instructions are tree address instructions. So they have, for example, add on ARM has 2 inputs and 1 output operand. But on x86, add is a destructive operation that uses 2 input operands, and the first operand is also reused for output. And so we have to be able to translate between those two. The way that we do this translation is what we call a splitting pass. So the goal of splitting is to make the job of subsequent code generation passes easier. And so basically with splitting, we break down complex instructions into simpler ones. We do a little bit of pre-chewing and normalization as part of splitting. And this has to be done differently for each architecture based on the limitations of each architecture. Like I said earlier, our intermediate representation uses 3 address instructions, but x86 uses 2 address instructions. And so in the splitting for x86, we do the conversion from 3 address to 2 address instructions. And we do that by introducing extra moves where necessary. Also, ARM only supports small immediates or constants in the machine code. So if we're not able to encode an immediate in an instruction, we have to split the instruction. And again, we do this by adding extra moves when necessary to load constants into registers. So now I'm going to go over a simple example. So suppose we have a function here, foo ab, which produces the sum of a and b, and then we call this function foo with the values 1 and 2. And here at the end, I've added a call to Yjit disasm, which is going to list the machine code that's generated for the method foo. So the first thing we're going to look at is the bytecode for this method. So we have two get local instructions to get the values a and b and push them on the Ruby stack. Then we're going to call opt plus. And finally, we're going to do leave, which is going to return the result. And so in terms of interfacing with the backend, here I have a list of code with Yjit prior to the implementation of the new backend. So the first thing that we do is that we have a guard to check that both values are fixed nums. Then we're going to read the operands a and b from the stack, so we're going to pop them off of the Ruby stack. Then we do the addition of both of the input operands, and we do an overflow check. So we checked that the results of a plus b does not overflow what can be encoded as part of a fixed num. And then we're going to push the output on the stack. So here you'll notice I have a move and a subtraction and an add. The subtraction of 1 here is just so we can maintain the tag bits. So fixed nums have the lowest bit set to 1. So by doing a subtraction here, I'm removing one of the tag bits from one of the integers so that I can maintain the fact that the lowest bit is always 1. Prior to the implementation of the backend, we had to manage temporary registers by hand. So here we're using reg0, which was the RAX register on x86. With the new backend, the code looks like this instead. So as you can see, it's pretty similar with the difference that we're now using an ASM object. And also, instead of using registers, we have named operands that we can use for temporaries, and we can take the output of an instruction and feed it to the input of another instruction. And in terms of machine code, the machine code that gets generated looks a little bit like this. So we use the test instruction on x86 to check that the lowest bit is 1. And if the lowest bit is not 1, because the input is not a fixed num, we jump somewhere out of line. And then we check that the second operand is also a fixed num. Then we do the addition of the two numbers with the subtraction and the jump on overflow. And then finally, we write the result back on the stack. Here we have a listing of the code that we generate on ARM for this same fixed num addition sequence. As you can see, it's quite a bit longer and not as pretty as x86. So part of the problem here is that ARM is a RISC architecture, and so it needs more instructions to achieve the same functionality. Another part of the problem, though, is that when we're doing the guard to check that the values are fixed nums, and also when we're doing the overflow check, we need to jump out of line. And unfortunately, the sequence that we generate for jumping out of line currently is fairly long. The reason for that is that we need to jump pretty far, and the lengths that we can jump on ARM directly as part of a conditional branch instruction is something like 1 megabyte. But the code that we need to jump to is located farther away in memory than 1 megabyte. So in the future, I think we can address that by redesigning the way that Yjit stores out-of-line code so that it can be placed closer to the code that we're generating. And so here we could have a much shorter sequence of instructions. But as you'll see, we still get pretty good performance despite this. So there's some good and bad news here. I would say the bad news is that the generated code is relatively poorly optimized. So there's no register allocation for stack values. Our encoding of jumps on ARM64 is very inefficient, and there's many obvious optimization opportunities. But the good news is that the generated code is relatively poorly optimized. And so we're just getting started, and we're already getting pretty good speedups. And there's many obvious optimization opportunities that we haven't yet explored. So I think this is pretty encouraging, because as we do multiple improvements to the code that we generate, the performance can only get better from here. Now let's look at some performance results. So here we have a graph where each bar represents speed up compared to the interpreter, and higher is better. So the first bar compares the x86 new backend compared to the interpreter. The second bar compares the old Yjit implementation on x86 compared to the interpreter. And the third bar compares the ARM64 new backend compared to the interpreter running natively on ARM64 on my M1 laptop. The x86 results were benchmarked on an Intel CPU on an AWS instance. And the benchmarks used are Active Record, HexaPDF, the Liquid Template Renderer, the MailGem, the PsychGem, and RailsBench. And so what we can see here is that even though the code we generate on ARM64 is not that efficient, we actually get bigger speedups on ARM64 than on x86 on most of these benchmarks, which is pretty interesting. The second thing to notice is that the performance of the new backend on x86 is pretty close to that of the old backend, but it's a little bit slower by a few percent. This is because the code that we're generating on x86 has a little bit of inefficiencies in it, because the new backend tries to do more things automatically, but it hasn't been fully finely tuned yet. But as of the time that I'm recording this talk, these results are actually 2 days old, and there's a couple of pull requests that have already been merged to improve these results. So by the time you're watching this talk, we'll be even closer with the performance of the new backend and the old backend. And my expectation is that by the time Ruby 3.2 is released, the new backend is probably going to be performing the same or even slightly faster than the old backend on x86. And so in terms of current status and expectations, we just got the new backend working. The performance on x86 is a little bit behind the old backend by a few percent, but we think it's going to surpass the old backend. And this should very much happen in time for Ruby 2.2. I should also mention that ARM64 support is not as well tested as x86. If you try to run Yjit on ARM64, it's possible it could crash. If you encounter crashes and segmentation faults, bug reports are very helpful to us because we might not actually know that the backend is crashing on your workload. But if you file a bug report, please provide us with as much context as possible. For example, which operating system you're running, which CPU you're running, which command you use to start Yjit, and more about the specifics of your workload as well. We might also appreciate your help in debugging your particular circumstance. I would also say that at this point, ARM64 performance is competitive with x86 in terms of the speedups we're getting, which is very encouraging. So looking forward, in terms of next steps, we want to optimize the new backends. We want to improve the quality of the code that we generate. We also want to improve compilation speed, so the speed at which Yjit generates machine code. We're also going to work on implementing CodeGC this year. I'm hoping that we'll be able to include this in Ruby 2.2. This would go a long way towards improving the memory overheads of Yjit, which would in turn make Yjit a lot more suitable for production deployments. Next year, I think we should look at register allocation for stack values and locals and method call inlining. This would also have the potential for much bigger speedups. So in conclusion, this year we've been building a solid foundation to extend Yjit. We've been working on several improvements to Yjit, including the new backend. The new backend, I think, is key in increasing the adoption of Yjit because it gives us the ability to support natively all Apple hardware, as well as Raspberry Pi, AWS Graviton, and more. The new backend and ARM64 support are still experimental at this point. We just got it working, but we think it'll be ready in time for Ruby 2.2. And of course, you can help us find bugs and report them. Next year, we'll shift the focus back to performance work because I think that performance is key for Ruby to thrive and to grow stronger. So if you'd like to learn more about Yjit, there's 3 published papers and several recorded conference talks available on YouTube. There's a talk I gave last year at RubyKaigi 2021. There's also a talk that I gave at VMIL and the accompanying paper. And there's, of course, the original papers about basic block versioning if you're more curious about the technique. You can reach me by email or Love to Code on Twitter. And there's also a Slack channel on the RubyLang Slack that you can check out. So that's all for me. Thank you very much and have a great day.